would like to call Team EVOLON, which is a team of 12 members, brings you a propulsion system that will take a certain payload to our probable future planet Mars. So guys, please turn on your cameras and start the presentation. All the very best.
So good evening everyone. This is Team Avalon bringing you a mission to Mars, and these are our team members. I, Mohammad Atasam Ahmed, is the team leader, and Rishikesh is the assistant team leader. And we are a batch of 12 peoples, and our objective for the mission is to carry a payload of about 20 kgs from the lower Earth orbit to the 200-kilometer altitude above the Martian surface. To accomplish this objective, the first task was to select a payload. There were quite a bit of options for us available. These are some of them on the screen. We did a trade-off study on all of them, and as you can see on the screen, the Lyman alpha photometer and the TMC from Chandrayaan-1 had a better value for the trade-off that we did, and hence these two were selected. The Lyman alpha photometer was recently sent in the Mangalyaan mission, and TMC was sent in the Chandrayaan-1, and these two will be having their own individual tasks. After the selection of the payload, the delta V for the mission is calculated. To calculate the delta V, the basics of the Hohmann transfer orbit is needed. The Hohmann transfer orbit is a locus of all the positions that a satellite circular orbit to a higher circular one. In this case, the orbit of the Earth and the Mars are assumed to be circular, and the transfer orbit is the heliocentric one, which is elliptical. Once the Hohmann transfer is understood, we calculate the delta V using the equations in the previous slide. The calculation of delta V was done in two parts, from the LEO to HTO, the Hohmann transfer orbit. The value was 3.51 kilometer per second. For the second one, for the entering the Mars orbit, the value was 2.01 kilometer per second, and the final delta V value is 5.52 kilometer per second. The rest of the task can be will be explained by Rishikesh. To you, Rishikesh.
Thank you, Etsam. After deciding the delta V of our mission, we went on proceeding to the selection of the propellant. For this, we concluded the selection of the propellant by LOX plus CH4. Why we choose LOX plus CH4 was that because of its high ISPs and compared to the other bipropellant, and with the same value as the other bipropellant, it produces more thrust, and it is an non-toxic and non-corrosive propellant as well. And the high vapor pressure from this propellant provides an excellent vacuum ignition characteristic for the reaction control engines and main engines. But the hurdle after selecting the propellant was the zero boil of this propellant. So for the long stages, it was said that these propellants would boil off. But according to our zero boil off program, they have said that by using cryocoolers and protective shield inside the tank, we can avoid the boil off of this propellants, and we can take these propellants for the long distance missions as well. And after selecting the propellants, we went on discussing about the staging and the mass budgeting. For the staging, we used the ideal rocket equation, which is shown in the PowerPoint. And we further calculated all the stages, like for one stage mission, for two stage mission, and for the three stage mission. And by comparing all of these three stages, we came to a conclusion that we can go with the two stage mission, as it was efficient with the fuel compared to the rest two mission. They used less fuel as compared to the stage 1 and stage 3 missions. So we concluded on going with two stages mission. And after that, our main part came that we divided our teams into 4 separate groups. The first is system engineering, second is engine design, third is the tank design, and fourth is the feed system design. And about the system engineering, I would like Etsam to go forward.
So coming to system engineering, for our mission, it had 3 tasks. The first one was to calculate the thrust requirement for the mission. The second being the feed system architecture for the mission, and third being the mass budgeting with the practical values. For the calculus staple mission, The reason being, it has a weight very similar to our weight, as you can see on the screen. And we approximated the thrust by weight to 0.54. That allowed us with a thrust of 1100 newtons. The 1100 newtons will be provided by a 700 main engine, and 50 newtons from 8 individual thrusters will provide us with the remaining 400 newton. The 8 thrusters are necessary to have any altitude correction if necessary. Once the thrust requirement was done, the feed system architecture was the second task of the system engineering. And on the screen is our feed system architecture. We went with the gas pressurized system with helium as our pressure gas. And on the screen is our feed system architecture. Moving on from this second objective, the third objective was the final mass budgeting. This mass budgeting is done after the values we obtained from the engine design team, which will come in the upcoming slides. The practical value for the ISP is 353, whereas the ideal value was 380. That gives us the nozzle efficiency of about 92%. So that is the final mass budgeting of our mission. And from here on, the engine design team will take over. I would request Kayu to explain the part.
Thank you, Itesam. Okay, so in the engine design part, our main objective was to calculate the actual mass flow rate and the actual ISP of the engine, and also we have to calculate the nozzle dimension and the pressure, velocity, and temperature at each and every point of the nozzle. So basically, we went through these all equation step by step. We using this equation, and at the end we calculated the mass flow rate. From that, we calculated the ISP. Yeah. So from the system team, we got to know about we need a 1100 Newton thrust. So we divide 1100 Newton into two part. First, 700 Newton thrust for the main engine, and we use a 8 thruster for orbiter maneuvering correction. Each thruster have a thrust like a 50 Newton. So for the 700 Newton thrust main engine, our input was like our chamber pressure is 1.2 megapascal and our exit pressure is 1 kilopascal. Rest of the input you can see in the screen. From that, we calculated our all the throat data and our exit data. From exit data, like our exit Mach number is around 4.83 and our mass flow rate is around 0.202 kilogram per second, and our actual ISP is 353 second for the 700 Newton main engine. So we did same calculation for the 15 Newton thruster. From that, we found our mass flow rate for this thruster around 0.014 kilogram per second, and our ISP is around 353 second, which is quite similar to our ideal ISP. So from now, I would like to invite Mayuri for the further discussion about the nozzle length and the chamber design. Over to you, Mayuri.
Thank you, Keyur, for introducing me. So we selected bell nozzle type for our design, as the bell nozzle is compact, less massive. It reduces the divergence losses at the exit, and also we assume that the length of the nozzle should be equal to 80% of fractional length, because more than 80% does not significantly contribute to the performance. And whatever the calculations we did, and we got the parameters for the 700 Newton main thrusters, we use that parameters, and with ln is equal to 80% of LF, with that assumptions, we did some iterations and found the length of the nozzle and the required angles. And the length of the nozzle for 700 Newton main thruster came out to be 0.167 meter, and the ISP, as we got 353, so the nozzle efficiency is 92.6% we got. The same assumptions were made for the 50 Newton small thrusters also. For these also we use the previous calculated parameters, and the length of nozzle equal to 80% of fractional length, and we got the length of nozzle through iterations as 0.044 meter, and the efficiency of 50 Newton small thruster also came out to be 92.6%. So though this shows that our nozzle is efficient. Then comes the combustion chamber design.
For combustion chamber design, we use the parameters from nozzle, and also we did some assumptions. Like we did the graphical representation. You can see the graph between L by D ratio and the internal surface area. So our aim was selecting the L by D ratio which contributes least surface area. So for both 50 Newton and 700 Newton thrusters, we got the L by D ratio as 0.5, contributing least surface area. So with that assumptions and considering characteristic length as 1 meter, we calculated all the parameters using the equation shown on the PPT, and we got the length of the main engine as 0.045 meter, and that of 50 Newton thruster as 0.0381 Newton, and we assume the theta to be 10 degree for the calculation. So this was our chamber calculation. Next, the tank design calculation will be explained by Dilip.
Thank you, Mayuri. I am Dilip from Tank Design. So, in designing a tank, we had three major outputs, such as they are finding a material for the tank and deciding the shape of the tank, the dimensions of it. And for material selection, we thought there are three major properties we need to concentrate on. The material should have high tensile strength weight ratio and should have low thermal conductivity and should be well studied, and all the properties should be available and easy to obtain. So we consider using different compound materials, but the third point is missing in them. So we went on with the old-fashioned way, and we selected titanium 6Al4V as the material for our tank. And all the properties for the material for the alloy are given on the table. And for choosing the shape, we went with the spherical tank for obvious reasons, since it has a low surface area for a given volume, which would be a lot helpful in optimizing the weight of the tank and also helping to reduce the heat transfer with the surroundings. And it has less ullage volume compared to other tanks. So we went on with the spherical tank shape, and another thing, the spherical shape also seems to have the high structural integrity compared to other shapes. So once we got the fuel and oxidizer weight from the mass budgeting, we used the formulas shown on the slide to calculate the dimensions of the tank. We got the weight and the weight of the oxidizer and the fuel could be as shown on the slide. From those, we calculated the volume of the tank that is needed to contain these, and by using those volumes and by using the pressure value given by the engine design team, we calculated the pressure that need to be maintained in the tanks to be as 2 megapascals. Next slide. And taking a factor of safety of about 2.5, we took the max pressure to be around 5 megapascal, and using those inputs and the formula, we calculated the dimensions of the tank to as shown on the table. And that's it from the tank design team. Thank you for listening. And Jagdish from Feed System Design team will continue with his presentation.
Hi everyone, this is Jagdish. Thank you, Dilip. The main objective of our feed system was to determine the type of feed system required for our mission, and we have selected gas pressure tank feed system for our mission because it best suits for the requirement of our mission. And as previously mentioned, the total thrust of our mission is 1100 Newton, and gas pressure feed system is ideal for it, and it is not as much as complicated as the pump feed system. So we have selected gas feed system. These are the specification of the helium tank we have designed for the pressurization. Here we have assumed the volume of 0.2 meter cube and temperature of 85 Kelvin. And using those formulas, we have calculated the specification of the tank. Here we use the helium gas because it is an inert gas and has a less molecular weight as compared to other inert gases. The pressure drop is a main factor to study because it is very much important to maintain the pressure for a feed system. The it feed pressure drop is the difference between the pressure when connected to the 2 points in a network. There are many types of pressure drops in the propellant path. Those are storage pressure and dynamic pressure due to the when it is moving through the pipes, and the line losses, which includes friction loss in piping and the pressure drop due to the restrictions like walls. Yeah, as I had told, the due to the flow restrictions and the friction due to the surface of the pipes, the line losses occurs, and the discharge coefficient is the dimensionless number which is used to characterize the flow and pressure loss behavior of the nozzle and valves in the fluid systems. And those are the first formula is to calculate the pressure drop in the pipes, and the second formula is to calculate the pressure drop in the across the walls. Further, Aitesham will continue.
Okay, so to summarize it all, we all had a payload. We have selected two payloads, the Lyman alpha photometer and TMC. We calculated delta V. We divided ourselves among 4 groups, each groups with their own submissions and subtasks. We completed it, and to conclude it all, the feasibility of the propulsion system that we have built, it is based on the study of the ZBO development that NASA is undergoing. Once the technology is available, the propulsion system is feasible enough to carry a payload of 20 kgs to the Martian atmosphere. And before concluding, I would like to have before concluding, these are the meetings that we had. SSERD allowed us with the platform to interact with each other, to not only share the knowledge but also have some fun and bonding sessions, uh, as you can see on the screen. And before I conclude, I would like to show my gratitude to the SSERD team for the amazing opportunity that they gave us during the lockdown period. And apart from them, I would like to thank our mentor Rakesh for guiding us in the right path, and our coordinator Tejas for keeping up with us. So all in all, I would like to thank everyone involved with us, and a big thank you from the team Avalon to complete SSCRD team. Thank you. We are open to questions now.
Great job, guys. That's a beautiful presentation. So, audience, do you have any question for them? Uh, okay, so there is a question for you guys. Uh, Rehan is questioning. Can you please explain ZBL again?
Okay, so Rehan, I'll explain it. ZBO means the zero boil off temperature. Like, the cryogens usually are not suitable enough for carrying for longer missions. The Mars, from Earth to Mars, is a long mission. It's a very long mission. So cryogenics are usually not preferred for that. So NASA is trying to develop is trying to come up with a technology to make sure that the propellants, the cryogenic propellants, are reduced to as low as possible. Like, the boiling point can be reduced to as low as possible. The detailed explanation of ZBL is not in our, like, it's not in the scope of our internship. So that we can only provide the superficial knowledge on the development of the ZBO. I hope that answers the question. So
Yes.
again, before you go on to the next team, I would like to thank again, show my acknowledgement to SSCRD, and thank everyone who was involved with this team and with this internship. Thank you all.
Thank you all. Thank you all for listening. Thank you.
Okay, so